into three main subjects: power systems, power electronics, and machines. Those are the traditional power topics. And we're involved in teaching classes, doing research, and service to our professional organizations and society. These are all the things that we do. You can see them. They're self-explanatory. They're all good things. The faculty and staff in our area, myself, George Gross, Alejandro Dominguez Garcia, Kevin Korevi, Phil Krein, who's on sabbatical leave, Tom Overby, who's losing his voice, Pi, who is retired, but Pi comes in once in a while, and Robert Pilawa, who is in Sweden, and myself. And then there's about 50 graduate students, and between 60 and 75 graduates in power and energy each year at the BS level. These are the courses that we teach undergrad. The Techniques for Engineering Decisions is going on right now. This semester, Green Electrical Energy is both semesters. Power Circuits and Electromechanics, that should be 3:30. We downgraded it from 4:30 to 3:30. Electric Machinery Laboratory, that's in this laboratory room. It's only in the spring. 432 is an advanced version of that, which is only offered every several years. Power Electronics, offered only in the fall, and it has its own laboratory, which is also taught in this room. And our third component, Power Systems, ECE 476. And then we have special topics. Solar Decathlon is one. That's one that we have done several years in a row. We had many hybrid car projects for many years. We have done the other one. What's the one? The solar house. No, there's another one. Future Energy Challenge. Are we doing the Future Energy Challenge this year? Okay, somebody asked me if we were involved in that, and I wasn't sure. So we're taking a break on the Future Energy Challenge this year, as far as we know. Okay. At the graduate level, we have a course that is kind of like an entry level ideal for every grad student, which is heavy on the numerical methods, analysis techniques for large-scale systems, modeling and control of electromechanics. That's going to be offered, I believe, in the fall coming up. Power system operations and control, offered every other year. Power system dynamics and stability, offered every other year. Electricity resource planning, every other year. And here we are in ECE 590, which is the seminar. But then we have interesting topics that pop up. No official number yet. Those are some of the ones we've had in the past. Just in case you're curious, if you look at our output of students from 1950, where we only had about 25 graduates per year and only 3 master's degrees per year. And you follow these averages on through, here we are now at the 55 to 60 bachelor's level, 12 or so masters, and 6 or so PhDs. Oh, here we are. This is our laboratory. You recognize this because you're sitting in here right now. Activities, these are things that we do. We go to workshops. We go on review panels for research proposals. We go to this thing called CGRE, which is the, I'll just call it the European version of IEEE. We go to IEEE meetings, many of them. We go to which is their version, yeah, the U.S. version of CGRE. PCERC, I'll explain in a minute. And National Science Foundation, Department of Defense, Department of Energy, GCEP, that's the Global Center for, that's it, Stanford project. Solar Decathlon, these are just some meetings we go to. IEEE, we have really 2 societies, right? Power and Energy Society, Power Electronics Society, and actually 3, Power Industry Applications. Society. And we go to all of those. We have been very involved in a lot of IEEE activities. And PSCC, which is the European version of the IEEE General Meeting. Okay. Engineering Open House is coming up. So if you're not involved, see me, see Carl, see, we've got a lot of people involved in Engineering Open House, and we need more. 431 takes a class trip. We'll be going this year to G&W Electric. We go to conference expositions, North American Power Symposium, a lot of seminars we've presented here in this room, and we hold guest speakers. Just to give you an idea who our local companies are that support us, Ameren, of course, is our local St. Louis-based utility. Vitrode is a company that focuses very heavily on power electronics stuff. City Water, Light, and Power in Springfield. Continental Automotive is our tie to the... You're right. No, it's not. No. This is the municipality. Right. You're thinking Southern Illinois, or Illinois, whatever. Electrical Coil Winders. Exelon is the utility to the north, Chicago. Flanders Electric is actually a machines manufacturer, refurbishing in Indiana. We went there in 431 last spring. G&W Electric up in Chicago. Mid-American Energy, which is mostly Iowa. Power World, SNC Electric, Sergeant Lundy. They're here for the expo today. And Solar Bridge. Just an idea about finances. How much money are we talking? Not a lot. Maybe $60,000 to $100,000 a year that we get from those companies, but we leverage that money approximately 25 to 1 in other things. Funding other sources, the Granger endowments. There he is, the guy on the, if you read the paper today, that's William Wallace Granger there. And they have the Family Foundation just given us another $100 million for the College of Engineering. And so they are a huge reason for our existence. And this laboratory was remodeled by them in 1987. So that was almost 25 years ago when the first Granger money came into this department and university. PSERC, talk about that in a second. NSF, DOE, Homeland Security, Navy, Stanford is the GSEP. Okay, PSERC. Just to let you know what kind of things we do and opportunities for you. PSERC stands for Power Systems Engineering Research Center, and it's a consortium of these universities. Illinois was one of the founding 4, but it has grown to include, I don't know how many this is now, 4, 7, 8, 9, 10, 11, 13 maybe. It is funded by the National Science Foundation at a very modest level, just to keep the travel and keep us involved. It's industry fee-based. Every company pays $50,000 to be a member. We have about 40 members, so the income is about $2 million. That $2 million is spent on research in electricity markets, T&D technologies, which is hardware primarily for transmission distribution, and then systems, which includes all the algorithms and control centers. There's the website. They have a very good feature where all the students can upload resumes. If you want a summer internship, there's one for that. If you're looking for a permanent position, there's another place for that. You can go there and look for available internships. They're listed, and permanent jobs. You should all put your resumes there. I think last time we were pretty close to the largest university population for that site. But it's a great opportunity. It's free, no charge. We are also involved in a thing called CERTS, Consortium for Electric Reliability Technology Solutions. It's a Department of Energy line item, $5 million a year. There are roughly 5 organizations involved. Each get $1 million. Lawrence Berkeley, a private company, Electric Power Group, PCERC, that consortium, and Sandia Labs and Pacific Northwest. CERTS works on three different things: reliability, technology issues, real-time system control, reliability, and markets. Those are the three research areas for CERTS. We recently got involved in a $6 million Department of Energy project on the future grid. What is going to happen in the future for the electric power grid? And we were supposed to identify the electric energy challenges, control and protection issues, how do you integrate renewables and take care of environmental issues, how do you increase the workforce, and what about computational challenges, cyber physical systems, being resilient, and then broader analysis. What are the information and operating standards that are going to be needed for the new future grid? And we're working with the computer scientists and the computer engineers under a project called TCIP-G, which is a big project, about $20 million over 5 years. So it's roughly $4 million a year for 5 years. And it involves 4 universities, us, Washington State, Cal Davis, Cornell, Dartmouth. I think they each count as half. I'm not sure. 5 universities, I guess, if you count Cornell. Dartmouth, and we have an industry interaction board of over 300 working engineers that work with us. And the director is Bill Sanders. He's here at Illinois. That's the website. We have 4 technical areas. We're worried about wide area monitoring. We're worried about local monitoring and control, relays, protection. And we're worried about responding to cyber events, attackers and hackers. And then we do risk and security assessment. There are 3 cross-cutting areas. We have a test bed that covers all 4 areas. We have an interaction technology transfer effort to take this stuff and give it to industry to use. And then we have one on education and workforce, which is actually quite interesting, creating things for high schools and K through 12. Finally, let's talk about Granger's Center for Electric Machines and Electromechanics. Started and funded, of course, by William Wallace Granger's Family Foundation with a roughly $15 to $20 million endowment. That was given maybe 10 years ago. It exists here in this lab and in the power electronics. The focus is on machines and electromechanics, heavily involved with power electronics. We have collaborating universities: Berkeley, Georgia Tech, MIT, Oregon State, Ohio State, Purdue, and Wisconsin. Some highlights: look at actual stator rotor design techniques, new materials, new analysis techniques to do high performance energy conversion. And that's it. That was to let you know what our area is all about in general. And now we're going to go on with our official seminar with Kai. Anybody want to say any more about him than that?
Yeah. All right.
This is not Kai Strunt. Kai Strunt is
that good?
In Berlin. This is Kai Van Horn.
Hello? Yeah, all right. So, yeah,
Where'd you go to school before this?
I'm Kai Van Horn. I finished my undergraduate degree at Purdue, and then I was a master's student here until last semester with Professor Gross. And I'm continuing as a PhD student now. So, let me see. The ones that are white in the background there. All right. So today I'm going to be talking to you about some research I've been doing. It's kind of an extension of my master's thesis on the full impacts of demand response. So you read my titles, you read the abstract. But basically, what I'm getting at here is that when you consider a demand response curtailment, and I'll get to what that means in a little bit, that's not the full impact of the resource, and we want to kind of get an idea of what the full impacts are. So past studies in this area have looked at demand response in terms of the curtailments only. When loads reduce their energy consumption, what impact does it have for the market and for the system? But we want to consider the explicitly what happens if that energy then comes back at a future hour. And so the studies that have been done have not really looked at that, and when we look at that, we see that those benefits that have been reported are not as great as they had been reported to be. So in addition to that, we look at the incentives that are provided to demand response to participate, and we see that the incentives to participate are much greater than the benefits that are being accumulated by the system, and so it's incentivizing demand response or penetrations of demand response, which may not have the greatest benefit to the system. So just to give you a sense of what demand response is doing now, this chart shows the percent of the demand response penetration as the percent of peak load on the vertical axis, and then the various independent system operators and regional transmission operators in the United States. So we see that for the years 2009 and 2010, we had between 2%, which is ERCOT, the Electricity Reliability Council of Texas, and NISO, or PJM, around 10% demand response as a penetration of peak load. And so you see it's already a presence. I mean, this is the potential demand response, the demand response which is signed up for demand response programs. So we see that this is already a presence, and so to consider the impacts is already something that's like pressing upon us. So, like I mentioned before, demand response is a reduction in energy from what the expected consumption of a load was in response to an incentive payment or some signal from the ISO or the RTO to induce that reduction. And so we're talking about maybe in the peak hour. So right here is the system load for a typical 2-day period. And you can see that in the afternoon hours, the load is high. And so in those high load hours, typically electricity is more expensive, and so we have demand response curtailments to reduce the load in order to reduce those costs. And this is kind of where the picture has stopped. In studies that have been done in the past, they say, okay, this is the impact of demand response. But what we're looking at here is that, okay, no, it doesn't end there. When you have demand response curtailments, presumably that energy that they were going to consume before they provided the curtailment had some value, or why would they have consumed it to begin with? And so we say, or we're looking at what happens if that energy shows up later. So what are the impacts of this energy recovery? And so what we have is we have reduced system peak load, yes, but we also have an increased system base load. And so we have this whole modified load profile, and so we're trying to look at, for different penetrations, so different capacities of demand response, and for different amounts of energy recovered compared to how much was curtailed, what impacts do those have for the system economics and also for the emissions of the system as a whole? Yeah. So it's saying that, so you're saying that, like, what if they're just cycling, and so they're just allowing, so I mean, that would be more like, so basically that would be just a demand response curtailment without recovery if you're just cycling a refrigerator or increasing the set point of a thermostat. So I mean, in that case, if it's not affecting the consumers in any way, then yeah, then maybe you wouldn't see recovery. But for many loads, that's not going to be the case. If you're like maybe asking someone to curtail like a industrial process or something because they're going to receive a payment which exceeds the benefits they would get from operating the process, then maybe when the prices are low, they would want to recover that energy. But yeah, there are cases like that, and so in that case, we would have either low or no energy recovery. Yeah, we're talking. Yeah, I mean, even aggregations of consumer loads. So those are basically there's aggregations of small loads and there's large loads which are offering demand response. We're considering, though, demand response which is offered into the wholesale market, for the markets of those ISOs. So that's a segue into the electricity market clearing. So basically, the electricity market is where resources are scheduled in order to meet the supply-demand balance on the electricity system for those areas which are balanced by an ISO or an RTO. And so in those areas, suppliers of electricity submit offers which consist of a quantity of energy they're willing to provide and a price at which they're willing to provide it. And the ISO stacks up all those offers in ascending order and creates an offer curve. So each of these different colors would represent the offer from a different resource. And then buyers bid for a quantity of energy at a price. And where these two curves cross, that's the market clearing point. Now, typically the bid curve is represented as a mostly vertical line because most buyers are energy service providers which have an obligation to serve their retail customers, and so they're basically willing to buy energy at any cost in the market. And so this right here is one of the reasons why demand response has received a lot of attention, because basically no matter what the price is, they're going to buy, and so there's kind of you can see that if the generator offers are very, very high, then people are going to be paying a lot for energy, and it's kind of a deadweight loss of the economy as a whole. So when you have a demand response curtailment, you basically have a reduction in this load, which shifts the bid curve to the left, and you have a new market clearing point, which is lower than the original. And then likewise, when you're in the off-peak hour, when you have recovery, then you're going to shift that curve to the right, and so we have increased price. So this is the kind of DRR payback effect, which I refer to in the title. And this is it's this impact that we're really trying to investigate at over a range of demand response utilization scenarios. The FERC published a report in 2009 kind of giving a sense of what they expect is possible and what is what is likely and what is technically possible for demand response. And so they're kind of forecasting forward what they think the electricity load is going to be given different demand response scenarios. And so they consider the amount of demand response and then also the demand growth. And so this just gives a sense of what is going to come to be and what the FERC expects there to be. And the FERC is the body which governs the activities of electricity markets for ISOs and RTOs. So basically they expect that the load without any demand response and with a 1.7% demand growth to grow from 750 gigawatts roughly in 2009 to about 950 gigawatts in 2019. And then if we have just the same amount of demand response that we have now and the same demand growth, then that's going to be their trajectory. And so if we don't have any additional growth in demand response, we would still have 38 gigawatts in 2019. If we have some small investment in demand response programs and less demand growth, maybe through energy efficiency measures and such things, then we might have 82 gigawatts by 2019. And then increasing the amount of demand response which begins to participate. The FERC has a couple of more scenarios. But the basic takeaway here is that the FERC expects that the achievable participation, what the FERC says is likely to be realized, will be in the 4 to 14% range by 2019. So going from what we have now, 4 to 14%, that's a lot of additional demand response in the system, and so that kind of motivates why we want to understand not just the impact of those curtailments, but the full impact of those resources on the system. So kind of keep that achievable participation in mind as I go through some of the charts later. An additional driver of the demand response was a recent FERC order which changed the compensation or the payment or the incentive schemes for demand response. And so basically, prior to this order, ISOs had kind of a hodgepodge of incentive schemes to induce demand response to participate, but it was centralized, or it was made to be a single scheme now. And so now demand response is paid at the market price every time they provide a curtailment, provided that some price condition is met, which is predetermined. And if you want to talk about that, we can talk about it later, but I'm not going to get into it here. But what is important is that this order represents a significant increase in the incentives provided to demand response, and it's driving a lot of new demand response into the market. So, for instance, in the PJM, between 2011 and 2012, PJM was the first ISO to implement this order, and they implemented it in March of 2012, And so this shows the total demand response curtailments for each month in 2011 and 2012. And you can see that as soon as FERC implemented 745, that the amount of demand response that was cleared in the market, and in PJM's market, increased by a factor of 6, factor of 8. So this order has serious implications for the amount of demand response on the system. So the past work that was done in this area has been of a qualitative nature. Going back to 2003 and even before, there have been a lot of reports talking about the benefits in terms of improving market efficiency of using demand response resources or making loads more price responsive. And then going forward, there have been a few reports on the impacts of demand response that have been quantitative in nature, and the first of which was the Brattle Group's report, where they look at various amounts of demand response, mostly in the PJM, but then in this report they look at the United States as a whole. But basically they find price reductions in the 5 to 8% range. This one was reported in billions. My back of the envelope calculation was that that's about 5 to 7% of the reduction in the total payments for that year. But the takeaway from these is that they're based upon estimates of the price elasticity, and they focus only on the curtailment. And all of them conclude that DRRs provide a net benefit, even though, but they haven't looked at the impacts of energy recovery at any level, whether it be even just a small percentage of the energy that was curtailed. And so what we wanted to do with this work is to address that shortcoming, to look at what happens when you have energy recovery over a range of scenarios. So in order to do that, we're looking at the year 2010, and we take two test systems, and we're using data from MISO and from the New England ISO, and we're simulating the day-ahead markets rather than looking backwards and trying to estimate the price elasticity of demand, which is what is usually done. And then we're considering various DRR penetration scenarios of capacity, so increasing the capacity of demand response, looking at the utilization intensity, which we consider to be the number of hours per day that a demand response can provide a curtailment out of the total number of hours that are available for it to curtail. So for instance, if a business can only provide 2 hours of curtailment because they can't, without affecting their business, provide any more than that, then we would consider that, and maybe we consider if businesses can provide 4 hours or 6 hours, because there are a lot of things that can vary with demand response. And then we also consider energy recovery from 0% up to 120%, because demand response resources may even recover more energy than they curtail. There's nothing that says they have to recover only as much as they curtail. They could recover twice what they curtail. So we are looking at the economic and emissions impacts of this, and we're using the average locational marginal price for the buyers as our kind of common metric across the cases. And so that's just the total payments that people the total payments from all consumers over the year divided by the total load that was served. And by normalizing those payments, it also allows us to compare across the different recovery cases where maybe different amounts of energy were transacted. And we do the same for the carbon emissions, so there's some comparability between the cases. So I'm using the 57-bus test system, but it's modified to have an offer profile, which approximates the MISO's offer profile. And so I increase the number of generators so that we can approximate with higher fidelity the offer curve of the MISO. And then the load profile is also a scaled version of the MISO load profile for the same year 2010. And so I'll call this the S57 throughout. And we use the 118-bus test system with ISO New England data for the other cases. And I'm looking at 1 to 20% of peak load DRR capacity and 0 to 120% of curtailed energy for energy recovery, and considering whether DRRs provide 2, 4, or 6 out of 8 potential peak hours of curtailment. So those are the low, medium, and high intensity scenarios. So this chart shows for S57, the 57-bus test system, the change in the buyer average locational marginal price, the buyer ALMP, compared to the reference case, which I have down here, for deepening penetrations on the horizontal axis, and then each series of bars represents an increase in the amount of energy which is recovered. So the first thing to notice here is that the price impacts are less than 2% in all the cases. So, and that's even for the no recovery case. So, which indicates that in this system, the demand response, there's not very much opportunity for demand response to reduce the consumer prices, because even at 20% penetration, 20% of the peak load is demand response, we still only have 2% reduction in the prices. Next thing to notice is that we can see very clearly, which is what we expected, that energy recovery diminishes the price impacts of DRR. So for a given penetration, as we increase the amount of energy which is recovered, the price impact is attenuated. So, and also, as the penetrations deepen, that attenuation is more acute. So for instance, if we look at 2%, they're very similar between the no recovery and full recovery case. So in this case, you would have some generators in the off-peak hours which have some headroom that's not being used, and so those generators would be making up some of that recovery energy without increasing the prices. But as we move to the right here and demand response penetrations deepen, then there's going to be a lot of generation that's brought online in the off-peak hours to serve this new load, which is realized because of the energy recovery. And what happens is that as we deepen the penetration with energy recovery, we have diminishing returns of these buyer price reductions. So as we deepen the energy recovery percentage, the penetration at which we don't receive any further benefits from having more demand response becomes less and less. So at no recovery, we can, even up to 20%, there's always greater benefits from increasing the penetration. However, when you increase the recovery percentage, then, for instance, at 50% energy recovery, then somewhere around 10 to 12%, you no longer have any additional benefits from adding more demand response to the system. And in the most extreme case, when you have 110, 120, or even 100% at high penetration, demand response actually causes the prices to increase over what they would have been without demand response. So when you consider energy recovery, clearly the impact can be substantially different. You go from here, where you had a 2% reduction in prices, to when you consider that energy recovery, you have roughly a 1% increase in the prices. So, I mean, energy recovery is clearly an important component of the overall impacts of demand response. If we look at, so that was the medium intensity scenario, so we only had 4 out of the 8 possible hours of demand response curtailment. And so if we have 6 out of those 8 hours, you can see that we have uneconomic results at even lower penetration. So now even at 10 or 12% penetration, you have either almost no economic impact from the demand response, or these uneconomic impacts from the demand response. And so this is 10 to 12%. This is within that FERC achievable participation range up to 2019. So this is within the range that the FERC expects demand response to fall in the next 5 years. And the diminishing marginal returns begin even lower at 4 to 6%. So this means that the penetration of demand response at which the system receives the greatest benefits is only 4 to 6% if we have this high utilization intensity. And so this is a penetration which is already achieved. So basically, if this were to be the reality, then we wouldn't even want to incentivize additional demand response. We would already be at a point where the system is saturated. But on the other system, where we have a greater difference between the peak and the off-peak prices, we see that demand response actually has greater benefits. However, those benefits are still extremely affected by the consideration of recovery energy. So we have here that the price reduction is roughly $6 out of 63. So it's about 8% reduction in the prices on this system, and so that's kind of in line with those other studies that I mentioned earlier for the no recovery case. However, when we consider energy recovery, then around 12 to 14% we see these diminishing marginal returns. And even though we have price reductions of 1.5 to 10%, we have decreases in the prices by as much as a factor of 6 when we consider energy recovery. So even in this range here, the 12 to 14% range, you have 40, even 50% decrease in what you can realize in terms of price reductions when you consider energy recovery. So another important component of this, too, is what benefits or what incentives are being provided to demand response, since the incentives drive the penetration of demand response, which we actually see on the system. And so those benefits consist of 3 distinct components. One is the value of energy that they don't consume. So whenever a load reduces its energy consumption, it no longer has to pay for that energy. And so in a way, that's a benefit to that load, that it didn't have to pay that high price. In addition to that, with 745, they receive an incentive payment. So not only do they not have to pay for that energy, they actually get paid the price after that reduction for not having consumed it. So for every megawatt hour they don't use, they're getting a price. And then you subtract from that the cost of the energy which is recovered. So the takeaway, though, is that the economic benefits to the DRR curtailments far outweigh those to the system. So you can see here for S57 with the high utilization intensity that in all cases, across all recovery percentages, you have monotonically increasing benefits to the demand response. So even if the demand response were recovering more than it curtailed and the penetration were 20%, they would still have greater benefits by increasing from 18 to 20% capacity. And so for the system-wide benefits, though, the onset of diminishing returns is down here at 4 to 6%. So if the incentives are to increase the penetration or to bring more resources online because they're getting additional benefits, but the system has its greatest benefits down here is kind of a mismatch. And the potential for penetrations at which the resources become uneconomic is around 10 to 12%. So you see like this kind of a mismatch of the incentives that are provided to the demand response and the benefits that are accumulated to the system. And even in the case of the 118 bus system where we had great benefits, there's diminishing marginal returns of the DRR benefits, but they're still monotonically increasing. And so even in this system where we had around 12 to 14% to be the penetration at which the greatest benefits to the system were achieved, that's not where the incentives are pushing the demand response to be. So in the summary from these economic impacts is that as you increase the DRR penetration, you're decreasing the average LMP and increasing the DRR benefits when you don't consider energy recovery. I mean, I think that much is clear. If we reduce energy, then it costs less. But when you consider energy recovery, then at some point you reach a minimum price, or a greatest benefits price, and then after that you can have these price increases. And same for the DRR benefits. I mean, at some point, even though this doesn't ever go back down, at some point it would go back down. It's just that it's not within what the FERC considers to be the technically possible range of demand response. And for demand response intensity, the number of hours that they are providing that curtailment out of the number of possible hours, it's pretty much the same picture. So when you don't consider energy recovery, everything's great. When you consider energy recovery, then you can see that we can get to this point where demand response, the system's actually worse off with demand response than it was without it. So we also want to look at the emissions impact. So we used capacity breakdowns that are roughly that are representative of the ISO. So this is kind of like the MISO, very coal heavy. And this is kind of like the New England ISO. It focuses mostly on natural gas. And then I assigned them to the offer curve in this order, nuclear units being the cheapest, and then renewables, coal, natural gas, and then the oil-fired units. So then using that loading order, you can calculate the emissions impacts of the demand response. So for the 57 bus system, we see here that the first thing to note is that the emissions increase in almost all the cases. And what's happening and what's causing this emissions increase is the fact that this system is a coal-heavy system, and coal is loaded before natural gas. And demand response curtailments, like I showed in one of the first slides, normally happen in the peak hours when the load is high. And so the units which are being used to serve that load are the units that are at the top of that price-based loading order. So they're going to be the natural gas-fired units and the oil-fired units. But in MISO, there's not really any oil-fired units. So it's natural gas-fired units which serve that energy. And the units which serve the energy recovery are typically the coal-fired units. And so basically what we've done is we've shifted energy from less polluting natural gas-fired units to more polluting coal-fired units using demand response. And so from a perspective of emissions reduction, demand response right off the bat is a loss for the system. Even in the case when we have no energy recovery, there's some slight increases here. This is just congestion effects that are intervening there. But you can see that as we increase the penetration, this is shifting back more or less energy from natural gas to the coal. And so as we increase the penetration, we actually see kind of better results over here. But overall, even though the emissions reductions are very small, there's still increases. But the other takeaway is that DRRs don't really impact the emissions that much. And so they're not really, even though they're a negative impact, they're not a huge player in terms of like an emissions reduction strategy, either for or against increasing or reducing emissions. So, but the opposite is true actually on the 118 bus system, because in that case we were a natural gas heavy system which had a larger percentage of oil-fired units which are being used to serve those higher load hours. And so we're shifting now generation from oil-fired units to natural gas-fired units, which results in emissions reduction since natural gas reduces or emits fewer CO2 emissions than oil. But even in this case, even though the emissions reductions are small, below 2%, the energy recovery severely diminishes them. So you see, in this case here, we're going down by like a factor of 9. It's like when you consider the energy recovery, it's almost as if there was no impact at all in terms of the reduced emissions. So in one case, we have a system where emissions are increased. In the other case, we have a system where you basically don't have any impact at all. So in the end, I think that it's pretty clear that emissions, or not emissions, but the emissions and economic impacts are heavily dependent upon this amount of energy that's recovered, and that in order to make a full assessment of the impacts of demand response, this is an essential component. And that even at the medium to high intensity scenarios with modest recovery percentages within the range that the FERC says is achievable, and at low recovery percentages or recovery percentages that aren't even like full recovery, we can see these uneconomic outcomes or severely diminished outcomes, and we can see negative impacts in terms of emissions. So I can take questions now if anybody has any questions. Well?
So when you're assessing the return, you're looking at the average rotational workload, right?
Correct.
But as you see the increase in penetration, though, you also see a monotonically decreasing the peak loading of the system?
Yes, it would be. Well, it would depend. So what will happen is if when the penetration of demand response deepens, you're shifting energy to the off-peak hours. So in a very extreme case, you can almost have an inversion of the load profile where you have low loads in those peak hours because you've reduced them, but since those demand response since I'm trying to assess over a range, I'm requiring those curtailments to be recovered at some percentage, and so it can push up those off-peak loads. So either it will flatten or...
At some point, so you would expect Payback to occur from reducing investment in additional generation and transmission. Some demand response penetration maybe by reducing the total load.
Oh yeah, that is a good point. It's not something that I was assessing here. The benefit in terms of, I'm looking at the short-term benefits in terms of price impacts in the market. So there are several additional benefits that one of them you mentioned, which is reduction in transmission loading, deferring the need for additional generation or transmission assets, and also there could be additional benefits if we're looking at systems with lots of renewables. Yeah. That certainly is one additional benefit that could add to the benefits of demand response. But
yeah, even at higher levels of penetration,
Mm-hmm.
At those high levels, it's put the growth and level.
Yeah.
And so then at that level, theoretically, you prefer that.
Yeah. So that would basically shift all these points where it's maybe not good to have demand response. It would shift it all to the right, so you could have deeper penetrations of demand response and still have overall benefits to the system.
One of them is make sure you don't see it another peak at night, because then you have to put in generation just to be able to serve that.
Any other questions? Oh. Mm-hmm. Mm-hmm. Well, it's actually the curtailments are price-based. So the payments to demand response depend on whether or not a certain threshold price is met. So basically, I assume that nobody wants to provide demand response if they're not going to receive that payment. And so anytime that threshold price is met, then the demand response curtailment occurs. But I do restrict the hours of the day that they can occur to 8 because there's not really any demand response curtailments in the off-peak hours now. And so it's price-based. So it's not that, I don't say they're happening in all these 1 hours. I say there's a period of time that they can happen if this price condition is met. Any other questions? All right, thank you.